we're going to talk about compliant mechanisms today, but I might also digress a little bit to talk about structures at the beginning. And if we have time in the end, I might also talk a little bit about structural simulations in morphine materials. So just a quick preview of what we're going to talk about today. So as I said, we're going to talk about structure in general first, and it's also a chance for me to introduce myself, I guess, like how I perceive structures in different fields that I work in. And then we'll jump into compliant mechanisms, and followed by one of the projects I led in the past year about reconfigurable compliant mechanisms. And after that, I'm going to show a couple of explorations that we did with compliant mechanisms and morphing materials. And finally, we'll narrow down to more specifically wearable compliant mechanism devices for different human or computing purposes. All right, so structures. So I'm actually an architect by training, and in architecture, we define structures as the load-bearing system. And this is specifically for modern architectural design, because in more conventional or vernacular traditional architectural design, it's actually a different deal. But structure in architectural design, or design in general, I guess, is the load-bearing system. However, in other fields like physics or material science, structure defines the arrangement of constituting elements like atoms, and these structures actually serve a different functional purpose. So they would actually define or dictate how your materials or polymers would have certain properties and things like that. And interestingly, in physics, they also call this arrangement of atoms information. So it's not that relevant, but it's something interesting to know. And in computer science, structure, especially data structure, defines the arrangement of bits or information, and they're usually arranged in a certain way that makes it easy to process. And for example, if you're writing an algorithm, you actually have to think carefully about how you arrange or structure your information so that your algorithm runs efficiently. And in HCI, there's actually a duality between physical and digital structures, meaning that we're interested in making things physical, but at the same time, we're trying to capture a digital representation of the structures. So for example, concepts like digital twins, where you have a physical object and you have a digital representation of that for tracking it, allows you to do a lot of things like real-time computing. And also we're interested in making digital tools for these physical objects or structures. And just to give a few examples of what HCI researchers have been interested in. So this is metamaterial mechanisms. It's led by Professor Alexandra Ion, who is now at CMU HCII. And they're using a grid-like pattern to create functional structures. And in this case, it's actually a compliant mechanism. We're going to talk more about that later, but just take it as is. And these structures are easily printable with a 3D printer. So there's also something that we are interested in. And I believe from the past lectures, you probably know that this is also something that we are in the Morphing lab are interested in as well. So what they did in this project is they have figured out this way to design these compliant structures with these grid-like patterns, and they've made a design tool to assist users to create these structures from pretty much nothing, from ideation to product. Yeah, I'm gonna move forward. And in another project, they take this idea further. So in the previous project, the entire structure is passive, meaning it doesn't carry out any computation at all. It's all controlled by the human user. But in this case, they actually used the same, pretty much the same mechanism, but they added a few buckling structures to simulate how information is being computed in a computer. So in a way, this is a mechanical computer, but different from conventional computers where information is stored as bits and bytes. In this case, they're stored as deformations. So that's also something that HCI researchers are interested in. And there's something more on the computer graphics side of things. So this is a So this is a project by Disney Research where they develop an algorithm to convert a conventional linkage system, basically a system made of rigid bars and hinges, and convert it into a compliant mechanism. So there's also something that people have been interested in. And really from here, you can see that I'm trying to find a few examples of compliant mechanisms in HCI, and it's actually a rising topic in the field. So why does structures matter to morphing materials? Well, my answer, or my short answer, is that they're a way to arrange media into functional blocks. So you've probably seen this from previous lectures in 4D printing or shrinking or shared memory polymers. So we have a material and we're using, for example, fabrication methods like 3D printing to structure them into functional structures. And we are designing things based on these functional structures to derive even more complex, say, functions or application scenarios. And this is actually a recursive relationship. So if you're familiar with the concept of fractals, I would say it's actually more or less similar, because at the bottom level, you have the materials and you're structuring them into building blocks, which you can even composite more building blocks together into functional primitives and so on and so forth until you get the final object. And that also means you can break an object down all the way to the material levels. And in between the materials and the final products or the objects, you're just designing structures in different resolutions or scales. So from all the way from decimeter to micrometer scales. So that is the role of structures in morphing materials design. And the concept of compliant mechanism is a slightly different way to design structures with how do you call it? Kinematic deformations. That means like using structures to design things that can actually move or morph in certain way while being stiff in the other directions. But we'll talk more about that later. But let me first give you a quick introduction to compliant mechanisms. So this definition is excerpted from the Handbook of Compliant Mechanisms. So it's an iconic textbook for this field. And if something bends to do what it's meant to do, it is compliant. And if the flexibility allows it to bend also helps it to accomplish certain things, then it's a compliant mechanism. So in short, compliant mechanisms are machines or mechanical systems that move by bending. That is different from conventional mechanical structures like hinges, bearings, or sliders, where they're actually, moving by, for example, two things rubbing each other, and you need a lot of lubricants in this scenario. But in this case, I'm showing a couple of daily examples of compliant mechanism. So for example, on the left, the bottle cap is actually a compliant mechanism because they have these rotating hinge right here that's actually allowing you to open and close the bottles by rotating on that joint. And also spring is also one type of compliant mechanisms. They're extending or compressing by bending the elements here. So that is a short introduction of compliant mechanisms. And actually, to be honest, everything is a little bit compliant because there's one saying in architectural structural design where every rigid part is to some degree soft and vice versa. And this image here is showing what I think is the Tacoma Bridge. Basically, it's one of the earliest suspension bridges built in the States. And as you can see, a bridge should be stiff and rigid, but in this case, it's actually twisting and bending a lot with respect to side winds. So everything is to some degree compliant in nature. And in compliant mechanisms, we're just leveraging this property to design functional structures. And there are also a couple of examples of compliant mechanisms in nature. So in this case, we're showing a trapezoid ant. It's basically, So this end has a
meters per second squared,
let's
which
watch
is
the
about
video
10
first.
times faster than a fastball being hit by a bat. It is one of the fastest movements of any known animal. I told you Mildred was a badass. And you know how she does it? A good clenching. Here's what one of her mandibles looks like up close. Kind of like a recalled sex toy. Jerry, show them what you made. It's a bit easier to understand. Roughly speaking, there's three main components to Mildred's trap jaw. First, when the mandible is opened wide enough, a little sticking out part slots into a groove. Next, the mandible closing muscles tighten. Because the mandible is held in place, this builds up potential energy, both in the muscle, but also by deforming the skull of the end.
Yeah, I'm gonna pause it right there for a little bit. So here, the skull is actually deforming a little bit, bending, denting to store certain elastic energy so that when the mandibles release that energy, they can snap really quick.
Finally, given the appropriate signal, another muscle releases the mandible from the catch, and then they pop right up.
All right. So that's the trapjaw end. So they're using compliant mechanisms on their skulls or their exoskeletons to trap and release energy to achieve a fair speed.
This motion is in.
And there are also like other examples, like in this case, we're showing I think it's a desert locust. So they actually have this joint on their legs that prevents the legs from snapping when they fail to jump upward. Because really the last thing you want when you fail to jump is to break your limbs. So that's what the locusts have. So they actually have a compliance section here on their legs that, for example, when their leg slips, when they're attempting to jump, because locusts actually jump with a lot of energy packed into them. So when they fail to jump and their leg slips, this compliance section right here is actually deforming to absorb all the energy that didn't got released properly when the locust was attempting to jump. And that helps them to, keep their limbs when they fail to move. So that is also a different use of compliant mechanisms in nature. And there are also compliant mechanisms in the human body. And
vessels, even contractile beating ventricles. And we've used that together with collagen and human stem cell derived cardiomyocytes to start to build.
So here you can see that this is a heart valve. It's basically the valve that is a part of your heart that prevents blood from backflowing to, the places where they come from. And it's actually compliant. And by that, I mean, they're actually bending to allow the liquids to move through. And they have certain geometries to prevent the liquids from moving backward.
Build functional pieces of tissue that contract, valves that open and close, and really multi-scale blood vessels. Moving forward, what this means is that we now have a foundation.
But anyway, this is just one example of compliant mechanisms in the human body. But actually, to be honest, anything that is not your bone is compliant in your body. So they're abundant. I mean, compliant mechanisms are abundant in nature and also in the artificial world.
Vessels, even contractile.
But finally, compliant mechanism hasn't been a huge topic in the field or in mechanical or pretty much in engineering until 1970s or 80s, because, well, compliant mechanisms are difficult to design. But they found their places in microelectronics fabrication because, compliant mechanisms doesn't require living hinges or sliders to move certain components. And in microelectronics fabrication, this is particularly favorable because, making things in that scales means you practically cannot assemble anything together. So you really want to make things as a single piece without moving parts. So compliant mechanisms research has developed a lot in the 70s and 80s, and it's still going on. And they have certain benefits like allowing us to make things small because you don't have to assemble things together, and you also don't have to include mechanical components like hinges and sliders. So that is good. And in this context, they're mostly using silicon as mechanical materials. And compliant mechanisms also offer certain advantages in mechanical structural design or design in general. They're very precise because they don't have living hinges or things that require a lot of lubrications and are prone to wear and tear. And they are also jointless. And as I said, that means they don't require, lubrication or things like that. And they're also monolithic, meaning you can make them as a single piece, which is especially favorable in application contexts like making satellites or thruster parts for things that enter the space. Because if you can make things as a single piece, you're going to save a lot of weight and complexity, and it's particularly favorable in harsh environments. So this video is showing a thruster made of compliant mechanisms, or the gimbal mechanism of a thruster made of compliant mechanisms. Conventionally, if you're going to make this mechanism, you're going to need a lot of parts and also a lot of hinges and a lot of lubrication. And because of lubrication, you can imagine this thing will go all out of work in a very short amount of time in space or in an extreme condition. But making things with compliant mechanisms actually makes them more resilient against harsh environments. So that's the advantages of compliant mechanisms. But on the other hand, they also have certain disadvantages or limitations. So while they do not have parts that are rubbing against each other, they're achieving deformation by bending. And that means it's really easy for them to become fatigued. And what fatigue means is that one example of fatigue is, for example, if you have a metallic thread, you can actually snap it into two parts by repeatedly bending it. And if you do it enough of times, you're going to snap it apart, and that is what fatigue is. And because compliant mechanisms are achieving motions by bending, so they're very prone to fatigue. And they also have a limited range of motion because, as I said, they're achieving motion by bending, and no structure can bend continuously in one direction. So you cannot, make a wheel out of compliant mechanisms because, you might be able to rotate it for, I don't know, like 720 degrees, but it cannot keep going indefinitely, unlike a wheel. And they are also very difficult to design. And this is really the bottleneck that's keeping compliant mechanisms from becoming a part of every product. And why they're difficult to design is because they involve nonlinear behaviors. So the plot on the right-hand side is showing different methods to predict the deformation of compliant mechanisms. So the circles right here is the physical measurements of how a compliant mechanism is deforming. And the line right here is a classic mechanical model to predict how these structures would deform, and is actually linear. And as you can see, it's matching pretty well at this region in terms of predicting the deformation of the compliant mechanism structures, but the error becomes larger and larger as the deformation goes beyond a certain threshold. And as you can see, the trend of these measurements is actually non-linear, and it makes these structures difficult to design. And they're also very unintuitive to design. Meaning there are certain principles like, for example, if you're designing a compliant mechanism and when certain things break when you're deforming it, like the common intuition is to thicken the structure so that it doesn't break that easily. But that's actually not the case in compliant mechanisms. In order to prevent something to break, you actually have to make it thinner. So that is counterintuitive. And it also makes compliant mechanisms very difficult to design. And you have to find other ways to strengthen the structures. And when designing compliant mechanisms, you have to design the motion and force and geometry at the same time. So it is a quite complex design domain. But anyway, in terms of designing compliant mechanisms, there are three ways to design compliant mechanisms, or three levels of design, I would call it. So at the bottom level, there are tools for analyzing how a compliant mechanisms would deform. And so, for example, if you design something, you can use these analytical tools to figure out how the thing you design can move or morph. And there are also another type of tool that's based on conversion, meaning if you have an existing conventional mechanical system, you can use these conversion algorithms to convert them into a compliant mechanism. But that means you need to have a conventional mechanical system at the beginning. And finally, we have synthesis. Is basically creating a compliant mechanism in nothing. And this is the domain that I work a lot in, and we're gonna talk about that later. But let me show you a couple of methods for designing compliant mechanisms first. So one of them is based on analytical tools. And in this case, they're developing a technique called topology optimization. So the concept behind this method is that you have, for example, a chunk of materials, and you try to eliminate like certain parts of the material one by one until it gives you the function you need. And there are certain smart ways about math that they introduce to this method to make it run fast. But the idea is you're using simulations to figure out, okay, this is the material bit that I don't need, and I can just take it out, and you do it iteratively until you get something for certain actions. So in this case, they have a square block of material, and they define the input and the output of the system. So if you push it in this direction, it's going to contract in the opposite direction. So it's a force inverter. And they're just practically just running simulations over again and taking materials bit by bit until you have the function you desire. So this is actually a slow way but accurate way to design compliant mechanisms, or in another word, it's a brute force method. And there are also another method that's based on conversion. So it takes a conventional mechanical system. They have a couple of living hinges and rigid bars on it, and convert it into one that's made of compliant mechanisms. And in this case, they're using this thin notch to replace the hinges you have here. And it's based on replacement or conversion. So the limitation here is that you must create a conventional mechanical system first and convert it into a compliant mechanism. So it's a multi-step process, and it could be a little bit complicated for common users. And finally, this is what I'm specialized in. It's called freedom and constraint topology. It's based on a kinematic school theory. Don't worry about these terms. This is just fancy words in robotics. But the idea is that if you know what motions you want, you can actually mathematically figure out what flexures or what structural elements you need to achieve that motion. And it is not giving you the solution directly, but it's instead, what is that? It's actually telling you like where you and how you should put the elements to achieve certain motions you want. And in this case, it's just a suggestion. So that means you can actually take these suggestions and generate different designs that achieve more or less the same thing. And that's what is shown down here, that the motion they wanted is a rotation along this axis. And the algorithms tells them where to place the flexures. And there are actually several ways to place the flexures to achieve the same motion. And that is the power of the effect method. And really, if you look at this, you'll find that this is a method that allows you to design things from nothing, meaning you define what you want as an input, and it will guide you through the modeling steps to create a compliant mechanisms. And that is what I'm doing a lot in our lab. And to give you an example, I'm going to switch to a different slide. It is one of the projects I did over last year. And let's see. All right, I hope everyone's seeing this fine. So in this case, we're not designing conventional compliant mechanisms, but we're actually making reconfigurable compliant mechanisms, which is actually new to the field. And we're using tensioning cables to achieve that. So kinematics, I've been using that term a lot, and what kinematic means in human-computer interactions is it defines the way how something moves, or in another word, it defines how something would move when a user interacts with them. And it is an essential part to our living experience. So for example, babies learns about the affordances of objects by actually tangibly interacting with them. And also it plays a huge part in our perception. So for example, you can tell what object you're holding by perceiving how the weight shifts in your hand. So kinematics is essential to that too. And it's also an important part to interactions in general, like how certain interfaces will move in certain ways will dictate, for example, how you play a video game or how you use an instrument. And in HCI, we are interested in making, we've seen this earlier, making functional devices that achieve certain motions, or we're interested in, for example, in virtual or augmented reality, we're interested in designing props that recreates the sensations of holding different objects. And finally, we're interested in using kinematics or to design morphable or tangible displays or interfaces that provides on-demand hand feels of interacting with different objects. But really, if you come to think about it, you often have to design like specific devices for specific type of actions and kinematics. And if you want to design a single device that affords the kinematic affordances of multiple objects, it's actually very difficult because that means you have to integrate like multiple functions together. And that could be unintuitive to even experienced engineers or designers, not to mention that for HCI researchers or just common people. And also, if you want to integrate these structures together, you're going to make the mechanical structures really complex. And at the same time, it's making it really hard to fabricate, assemble, and also it's really hard to design it to begin with. So really what we're proposing in this project is that we are trying to propose a method that uses compliant mechanisms to achieve mechanically simple structures. And we're using tensioning cables to design this to make sure that these compliant structures can provide different kinematic affordances when you reconfigure the cables in different ways. So that is what we're doing in this project. So just a quick definition of kinematics in 3D space. So an object in 3D space can move in two ways. They can either slide along one direction or they can rotate about an axis. And there are two types of motions, and these motions can happen along any of the XYZ axis. So down to the bottom, an object in 3D space can have up to 6 degrees of freedoms. And we've seen this slide before, but just a quick reminder, these are some daily examples of compliant mechanisms. So the compliant mechanism is typically made of two types of components. So one of them is these rigid components. They're rigid by their geometry, so they're more blocky, chunky, and they're more solid, and they're undeformable most of the times, but they can take any shape to provide any functional purposes. So for example, you can design the rigid stages into, for example, I don't know, like a handle or whatever shapes for gripping to make sure it's really easy for the user to hold onto the object. And because they don't take part in the deformation, so they're often ignored in the kinematics. Oops. Oh, my PowerPoint just crashed.
So yeah, folks, please feel free to interrupt Humphrey if you have any questions. I understand this could go a little bit abstract, and all the contents we try to show in the class are a little bit abstract to start with anyway. And we are gonna have a lab session this Thursday. That's about it. So we'll show some of the ways you can actually with your hand arrange some of the flexures and get different haptic feedback. Hopefully that will help you also learn more about this in a tangible way.
Yeah, and is everyone seeing the right screen?
Yeah.
All right, cool. And on the other hand, we also have these elements called flexures. They are actually the elements that are deformable. And in this case, or in this project, we're using flexural rods, which basically these long cylinders that have a slender aspect ratio. And they have certain structural properties here. So, oh, I don't think the video was playing, but okay.
It
Oh
is
yeah,
playing.
here, no, this one. So they have certain structural properties. So, well, what a bummer.
The slides crashed again.
Yeah.
It's PowerPoint, right? Not Keynote.
Yeah. How about I try something different? I will play the slides without making it full screen. Hopefully that will solve the problem. No guarantee.
Can you then, Humphrey, just move the slides a little bit or hide it so we can see the screen a little larger?
You mean?
Yeah. It's good.
Oh, I don't need that.
Great.
Yeah, so these rods actually have certain structural properties. So they can actually withstand compression and extension because they're more rigid in that direction. But they can actually bend or slide a lot when you're moving in other directions. And what this means is that when you have a structure like this, oops, now it's not playing. Well, this is supposed to be a GIF, but I can just talk over it. So what it means is that, for example, they can bend. So this upper stage will be able to move around. Actually, let me still try to play this. Oops. Yeah, there you go. So because they can bend but not compress or extend, so it determines how this top stage will be able to move when you put down these rods in certain directions. And there are also mathematical ways to predict, like, as I mentioned earlier, using the fact method, like there are ways to predict, for example, if you know what motions you want, you can actually use linear algebra to figure out what are the flexural layouts that you need to achieve to enable the motions you want. So there are methods to do that, and that is that. And here are just a few examples of how different layouts will give you different degrees of freedom. So here, when you have two rods that passes through the same point, it will give you 3 allowed rotations and one sliding along one directions. But if you have a different layout, like here, they're all passing through, I don't know if you can see this, but they're all passing through more or less the same line here that will allow only 1 degree of rotation. Yeah, there you go. So really, like, putting down these flexural rods in different layouts will give you different degrees of freedoms that you wanted. And you can make a design tool with the algorithms to help users achieve what they wanted. And then on the other hand, these structures are still not reconfigurable. So that's why we're adding tensioning cables. And tensioning cables have more or less the similar structural property as the rods, but they have an even more extreme aspect ratio. And this also gives them certain structural properties. So they cannot withstand compression. They'll buckle under compression, but they can withstand extension when they're tightened, and then they can also slide or bend along the other directions. And when you introduce them into
can I interrupt,
Yeah.
Humphrey? If you go back to the previous slides, so we're using some mechanical engineering terminologies here, right? If you're architects, you should be quite familiar with, you know, the words tension and compression. And Humphrey, if you don't mind playing the video again, but really what we're trying to say is, if it's a like flexible wire cable, you can push it very easily, deform it. But when you pull it, you cannot. So there's certain degree freedoms with a cable component. But if you remember how a rigid rod works, right? If it's a plastic rod, Humphrey showed earlier, you cannot push it. So there are differences in compliances, depends on what flexure elements you are using, cable versus rod.
Yep. And what this means is that when we introduce them in a compliant mechanism, especially when we tighten them, they will be able to lock these structures in. I have to play this. Yeah, they will be able to lock the structure. So previously it was bending, but now the cables are tightened and they're actually restraining the structure from moving. So the top part wouldn't be able to move when the cables are tightened. And in our case, we're using the motor to reconfigure the tightness of the cables. So when the cables are loose, the structure is actually free to move around however you want. But when you tighten the cables, they will become a constraining element that prevents the structure from moving. So really what this means is that if we be smart about designing the structures and using cables as a reconfiguring element, what we can do is we can first design a device with all the kinematic modes we want in a single device, and then selectively tighten the cables to achieve the kinematic affordance of different objects. So for example, in this case, we're showing the design of a multi-model input device. So depending on how you tighten the cables, it can either function as a twisting knob, a directional slider, or a joystick. And finally, we're also adding stretchable sensors to the structures to detect how the users are interacting with these devices. And these sensors are actually stretchable, and it's basically like rubber. So they're very stretchable, compressible, and you can bend them, twist them however you want. So they have no kinematic functions, meaning they don't function as a flexure element, but they're just there to pick up the deformation of the device. So, and as I mentioned, like compliant mechanisms are very difficult to design. And in this case, it's even harder to design because we're trying to design a reconfigurable device. So we actually made a computational design tool to help users to design the device they wanted. But I'm just going to leave it there just to so you know that there are design tools for that. But don't worry too much about it.
My understanding is we are not going to use the tool during the lab session.
We are
but
not going to use it.
The tool is available. So if any of you guys after the lab session, right, got very seriously interested in this kind of structure, feel free to reach us out. And we are actually interested in hearing feedbacks, how the tool, in terms of how the tool can be improved, actually, right?
Yeah. But anyway, just to give you a quick sense of how the design tool is helping the users to design the things they wanted. So it's providing a couple of things here. So it's providing a visual overlay over your models to show you like where you need to place your flexure elements to achieve the degrees of freedom you desired. And also it's using text to prompt you like what or how you should place these elements, or what are the requirements for achieving the kinematics you want to guide you through the modeling steps. So it's more like a modeling coach for reconfigurable compliant mechanisms, really. And the design process is divided into several steps. So that is, I think, is really easy to follow, but really we need more user studies to verify that. And when using a design tool or designing reconfigurable compliant mechanisms in general, we follow a couple of steps. So firstly, you need to specify what kinematic modes you want. And then you need to put down the flexural rods, and the design tool will then prompt you to add intentioning cables in the right places to reconfigure the devices. And you have the option to add in stretchable sensors to make this into a digital input device, for example. And these devices are really easy to make and assemble. And in this case, we're just printing these devices using a conventional desktop 3D printer. And the cables are adjusted using a geared motor and a reel to adjust the tightness of the cables. And for the multi-model input device, we're just using nothing more than an Arduino board to control the cable reconfiguration and things like that. Here, we're just showing a couple of design examples that we developed for these compliant mechanisms. And this video is showing a multi-model input device. So in this video, it's showing the device functioning as a slider. So the user can slide it along one directions, but the user would not be able to, for example, rotate it in the other directions or slide it in the, for example, perpendicular directions to where it's moving right now. And in this case, it's an input device. So we're using the slider to control the color of the background screen. And if you reconfigure the cables a little bit, in this case, it will function as a twisting knob. And that means they can rotate axially along the vertical axis. And we're using that to control the dial knob on screen. So it's the same device, but reconfigured with the cables are reconfigured. And finally, if you tighten and loosen the cables in a different way, it will be able to move like a joystick. And when it's moving like a joystick, you wouldn't be able to, slide it like we've seen earlier or twist it like in the previous video. So it's a multi-model input device. And really, because this class is inclusive tangible materials, so you can also think about these devices in terms of accessibility designs. Meaning, for example, people having certain disabilities might have troubles, moving their hands or their bodies in certain ways, and having a device that can change its kinematic functions depending on the user's limitations could be useful for accessibility or inclusive designs. And we also play with the idea of kinematic material displays. And in this case, compliant mechanisms are quite miniaturizable. So we actually ended up designing these textile bits or kinematic material bits that we put in that can, provide different kinematic affordances depending on how you loosen or tighten the cables again. And we'll just arrange them in an array so that the user can touch them and feel and have the hand feel of, touching different surfaces. So in this case, when the cables are loosened, the bits are actually quite deformable. And when you touch the surface or the array, it actually feels like touching something deformable like mud. But when you tighten the cables, the bits will become a lot less mobile and much stiffer. And when you touch the surface, it will feel like touching something rigid like dried earth. So you can change the material property or kinematic affordance on demand. And finally, you also play with the idea of providing haptic feedbacks for example, VR or AR applications. And in this case, we have a weight attached to the wearable device. And we're depending on, again, how the cables are tightened, they will provide different sensations of holding different objects. So when all of the cables are loosened, the weight is free to shift around. And when you hold it, it will feel like you're holding a cup of water where the center of mass of that water is actually shifting around a lot. But when you tighten the cables in one direction, the weight will only be able to shift in that direction. And when you shake it, you will feel like you're holding something that's only mobile in one direction, like a metallic ruler that can only swing in the more flexible direction. And finally, when you tighten all of the cables, the weight is practically impossible to move around anymore. And when you shake your hands in that scenario, you will feel like you're holding a rigid object. And there are possibilities to connect this to VR, AR applications. So for example, if you're playing a video game, depending on what objects you're holding in your hand, you can actually use these wearable devices to provide different haptic sensations. So that is the project we did in that research. And let me reshare my screen again. Oops, 1 second. All right. So if you think about it, like the examples I've showed earlier, they are just passive structures in the sense that, yes, their affordances are reconfigurable, but they are not morphing on themselves. Yet it requires a user in the loop, but because it's the morphing matter lab, so we actually thought about including like morphable materials into the structures to make them self-contained and self-functional. And in this case, I think you guys have seen shared memory alloys. So I'm not going to explain what that is. But in this case, we're designing a compliant mechanism skeleton, in this case, a gripper, And we're just adding, for example, these SMA actuators at the center to close and open up the fingers. And really, this is showing like how, because compliant mechanisms by convention is passive, meaning they will only deform when you interact with them, but you can add in like extra actuators to finish the job for you. And this is another example of an walker robot. So this is actually a walking robot that's designed out of compliant mechanisms. And in this case, we're using, these tiny, very thin and flat flexures to make sure the legs are moving forward in the right direction. This is a working prototype. And this video is showing the robot walking around just a very little bit. You have to pay like very careful attention to it to see moving. But anyway, in this case, we're using two shared memory alloy actuators to actuate two sets of legs at the same time. So when let's see. So when these SMA contracts is actually moving this leg, and this leg at the same time, and you can identify the groups by the diagonal rigid links. So we're using basically two SMA actuators to move basically two sets of legs in a certain way to simulate the gait of I don't know, like for example, a bug moving forward or things like that. But the message here is that you can use compliant mechanisms you can design compliant mechanisms to have certain properties so that it provides certain behaviors, like especially in robotics, to achieve certain functions like moving forward, backward, or turn around, or anything like that. And we also play with the idea of Biome compliant mechanisms. So if you're familiar with the TV series Westworld, they're in the intro video, they're actually showing how they're making the robots, and they're actually printing these, I think they are muscle threads onto a skeleton. And this is actually an idea we've played with before, but in this case, we're printing liquid crystal elastomers as the muscles. And I don't think we've introduced liquid crystal elastomers before, but it's basically a rubber-like material that will contract a lot and generate a lot of force when you heat them above a certain temperature. So in that sense, they're actually functioning like muscles. So here's an example, just to give you a quick sense of what LCE does. So these are a couple of LCE muscles we printed, and we're putting them in an oil bath that's heated to, I think, 65 degrees Celsius. And as you can see in this video, the LCE muscle actuators are actually contracting when you heat them up a lot. So what we did here is we take inspiration from biological creatures, in this case, a human arm, and put the muscle actuator on it. But in this case, when we're making the human arm, we're actually using a compliant mechanism to achieve it. So this is replicating the elbow joint of your human arm, and the LCE muscle actuator is actually functioning as your biceps in this case. And this is not specifically related to compliant mechanisms, but LCE actuators actually have a very high work capacity, meaning they can actually generate a lot of force. And you can be smart about the structures to derive larger deformations out of them. But I don't think I'll jump into the details. But anyway, just take it as is. So in this case, we're putting the muscle actuator at this position to simulate how the bicep is connected to your arm skeleton. And when the LCE contracts, is actually lifting the arm upward, and actually a lot. So that's something you can do with compliant mechanisms plus actuating materials. And I believe you'll see more examples of liquid crystal elastomers and deforming structures in the coming lectures. So I'm going to stop right here. Oh, actually, there's something more. So in the previous example, we're using the 3D printed skeleton to control how the structure would move. But really, like if you come to think about compliant mechanisms, it's all about the geometry. If you make something thicker and much blocky, it will be a lot more rigid than the other parts. And in this case, we're just using the same material. the liquid crystal elastomers, but we're playing with the geometry so that certain parts are a lot thicker, and there will more or less be the rigid stages in the compliant mechanisms. But the other parts are made a lot thinner, like this thin part, this thin hinge right here. And you can use that to create a completely soft skeleton, or in this case, we're just printing everything out of LCE. So it's, how do you call it? It's soft and deformable like rubber most of the times. And it will be like a soft animal, like, I don't know, like octopus or things like that. But the muscles here will be able to actuate the structures in certain ways to carry out certain functions. So it's different from the previous concepts where we're using a stiffer material to make the skeletons, and we're using LCEs just as the muscles. In this case, we're building everything out of LCE, so it's more or less of a soft animal, like, I don't know, sea slugs, squids, or octopus, or anything like that. And we also went a step further from just playing with, these bionic or bio-inspired materials. And in this case, we're showing a video of an actual biological material. And in this case, in this video, what we're seeing here is there's a harvested sea slug muscle. So that means we actually sacrifice the sea slug and take out I think it was the foot muscle of that sea slug, and attach it to a compliant mechanism structure. And the thing about these biological materials, especially animal muscle, is that if you shoot a current through it, it will be able to contract. And in this case, you can see the sea slug muscle is contracting to bend this compliant substrate. And the motion, again, the motion of the substrate is determined by like how you put down the thinner parts here. So that is something you can do with compliant mechanisms.
Yeah, just to add a little bit more about that, because I think it's it's unique. So so Professor Webster Wood, so she's a professor, runs a biohybrid robot lab at the CMU Mechanical Engineering Department. So I'm not sure if Humphrey made it clear. So actually, we sacrificed a sea slug on site. So she has a lot of fish tanks in her lab. Raise those sea slugs, and they are used for basically producing muscles. So she actually worked in the lab with us and literally derived a piece of muscle, contractile muscle, from the sea slug. So it is true, we didn't touch upon it earlier in any context, but it is true within the scope of morphing matter, we do consider living tissues and even living organisms as part of morphing matter as well. And it's a very active research field to study how real true biohybrid system can have some role in the future. Then you can actually leverage biological actuation, but even neuron computing for making morphing and intelligent systems.
Yeah, and since we're touching upon that, then I think there's one thing that's worth thinking about, especially for the designers out here. So people usually have an intuition that, these biological robots or biohybrid robots are cool, but people are struggling to find a good killer application context for these biohybrid robots, because in a lot of cases, the biohybrid robot, the conventional robot outperforms these biological or biohybrid robots a lot. And people are trying to find a good application context for these robots. So just food for thought. Anyway, and since we're talking about biological or biohybrid robots or structures, it is worth noting that the structure that these muscles are attached to are also important or are also critical to the performance of the muscles themselves. I'll elaborate. So in this case, this is one of the research out in the field where they're using a compliant mechanism skeleton. So as you can see in the graphs here, the skeletons can actually shrink or a little bit when the muscles are contracting. So the pink ring here is a 3D printed muscle around the structure. And the muscles actually mature by spontaneous contraction. So meaning when the muscles are growing and maturing, they will actually contract every once in a while. And if they are attached to a stiffer structure, they would tend to develop their contraction forces a lot more. So the skeleton itself also becomes an important part of how the muscle will perform when you culture them properly. So there are also research about that. So when using compliant mechanisms, so we were thinking about, like putting muscles on compliant mechanisms to actuate them, but really it's a symbiotic relationship, meaning when you put the muscles on the compliant mechanisms, you're actuating the mechanism, but at the same time, you're also helping the muscles to mature much better. So there's a biohybrid symbiotic relationship here, which I think is quite cool and poetic. And here's just a video showing how the muscles are contracting and how the structure is deforming. So I don't know if we have biomedical engineering students here, but there might be something cool to look into. And by the way, this method is a little bit different from the previous slide, because in the previous slide, we're harvesting like living muscle tissues from a sea slug. But in this case, we're actually growing the muscle cells in a lab controlled environment. So we're not sacrificing any animals using this, they call it the tissue engineering approach. I don't think, Linin, do we have a lecture on biological materials or not?
Plants only. There's not plant lecture on animals. So yeah, feel free to fill in more about it.
I see. But actually, I think I'm going to stop right here, because if I dive into that, it's gonna be a couple hours long lecture.
It just does remind me, I forgot, sorry, your name, but there is a student from our class. She has a biomedical minor. We've been chatting about how to combine her design and also biomedical tissue engineering side of interest. So yeah. for that student, if you are here now, there are work like this, and if you're interested, also feel free to check those papers Humphrey shared or chat with Humphrey.
Yeah, I've always wanted to work more in biohybrid robots, but unfortunately, I wish I have more time to work on different projects ideas, but we'll see. Anyway, and I was talking about like mechanical logic computers. We've shown that at the very beginning of the presentation. But here we can revisit the concept. So the current mechanical computer design methods are what we call functional complete. That means we can make several or basically 3 types of basic logic gates, all of these mechanical computers or design methods. So when we call a system functional complete, that means we can make an AND or NOT logic gates. And these are the basic logic gates you need to create any program. So if you design a system like this one in this image, they can achieve these 3 functions. You can put the logic gates in different orders to create different programs conceptually. But here the problem, especially for mechanical computer, is that they are program specific, meaning they're different from digital computers because when you make these mechanical computers, they can only carry out one computation and nothing else. So if you want to, create a if you want to run a different program, you would actually have to redesign your structure and print a different one so that it can actually carry out the function. But in digital computers, they are actually called Turing complete, meaning the same device can actually carry out different programs. So here's a visual comparison of mechanical computers and digital computers. So in mechanical computers, you have one structure or one artifact that can carry out one program. But in digital computers, you have one structure that can carry out different programs by reprogramming the flow of information or the structure of a computation or just the logic gates. So really in the Morphing Method Lab, we're interested in taking this idea a step further. So instead of having these mechanical logic gates single purpose, we're actually interested in using smart materials to make these logic gates reprogrammable. So what we're showing here is a mechanical logic gates that's made of compliant mechanisms but some of these flexures are actually made of a stiffness changing material. So what this stiffness changing material does is that when they're rigid, they function as a conventional flexures. So they will be able to, deform in certain ways, but at the same time pass forces along their axis and things like that. But when they're softened, they will lose the ability to pass on forces. And in this case, especially in mechanical computers, forces are the information or the bits of information. So if you can selectively soften and harden these flexures, they can actually carry out different types of logic gate functions. So for example, if you soften like two of these flexures here, they will perform like an AND gate. They will be able to pass information forward when both of the inputs are activated. But if you soften the flexures in different ways, they can either perform as a NOT gate, which inverts the flow of information, or an OR gate that as long as one input is receiving information, is going to pass that along to its output. So we're introducing stiffness changing materials as a part of compliant mechanisms. And we're actually working on this project right now. But yeah, I don't know where my speech is going, but this is something that's worth looking into, because conventionally, when people think about compliant mechanisms, we are still talking about like a single material that's passive, like silicon, metal, or just conventional plastics. But really, if you introduce like morphing materials or materials that change their properties depending on the environment they are situated in, there are a lot more things you can play with, especially in terms of designing the functions of these compliant structures. So I don't know, taking these ideas further, like for example, you might be able to design a structure that carries out a certain motion or computation in, for example, a hot environment. But when you put it in, I don't know, like a humid or cold environment, it will carry out a completely different function and completely different instruction sets. So something to think about. And I also want to touch a little bit upon like things that goes beyond shapes. These are not the things that I'm actively working on, but I think that might be relevant to people here. Because really, I think I could be wrong, but I think most of the things we discuss in this class are about shapes and how shapes change. But there are actually other things that we can play with as well. So for example, sound. So if you ever had experience with a music box, they're also one type of compliant mechanism.
Yeah, sorry, Humphrey. Can I just quickly interrupt you? I want to say it's 11:30 already. Okay. So we stopped the class pretty rigorously on time. I know you have a few more slides that are quite interesting. So how about this class? So again, we are gonna meet on Thursday in the lab, and you get a chance to interact with Humphrey also. I will let Humphrey continue, but I don't think, like the rest of the information, if you have to excuse yourself and leave right now, will create a huge knowledge gap. So feel free to leave, and I will also let Humphrey finish the few slides and wrap up.
Okay, I thought the class ends at 40, but I was wrong, I suppose. But anyway, I'll just keep going. So a music box is also made of compliant mechanisms. So it's actually making sounds by vibrating these freestanding flexures here. And the sound they make is actually determined by two factors: the stiffness of the material and also the mass of the freestanding flexures. So I'm interested in acoustics as a inclusive design element, because for people they are, for example, visually impaired or having difficulty to see things, sounds might be another way to convey information or to enable interactions. So there might be something worth thinking about. And also color is also related to structures, or more specifically nanostructures. So there are a lot of examples in nature that uses microstructures to create different sounds, to reflect different colors. So here is, I think, the structures on the claim that actually have these micro grooves or cavities that reflects lights of a certain wavelength that creates these beautiful colors. And there are also scientific research that is using, for example, the alignment of polymers to control what light they're reflecting. And really bringing this idea into compliant mechanisms, when you bend the flexures, for example, if you introduce these microstructures to the flexures, you might be able to, for example, when they bend, you might be able to control what wavelength they're reflecting. And thus you have a color changing compliant mechanisms at the same time while having those motions. So there might be something to think about as well. And finally, there are a few examples of wearable compliant mechanism devices. So these are the things that I'm more or less actively working on right now. And I'm actually funded by CMU's Center for Machine Learning and Health on developing design tools or methods for making medical exosuits. So the concept is that we wanted to develop a toolkit for designing these wearable devices that can, depending on what the patient or the user needs, and for example, whether it's providing rigid support on their arm or whatever. Sorry, this is virtual reality, my bad. So yeah, we've talked about this earlier. So we're interested in virtual reality as an application context, but anyway, we're still interested in developing the design tools. And because the hypothesis here is that it's really difficult to make a full body haptic suit, but if we can make a toolkit that's really easy to use for content creators to make like the specific haptic devices they wanted, we'll be able to, make virtual reality more tangible, I guess. So for example, you might be able to design a wearable device like this that can provide the hand feel of holding different weights in your hand on demand. And also you might be able to tune these flexure elements to make them sensors to detect how the user is moving their bodies and things like that. And on the other hand, I was saying that earlier, I'm actually working on medical wearable devices right now. And the use case here are rehabilitation and muscle training. And the limitation here, or why compliant mechanism medical exosuits are relevant, is because conventional medical wearable devices are customized and they are also very expensive. But if we can make things with compliant mechanisms while at the same time providing design tools for making them, it will make these devices a lot more accessible and customizable and even cheap to replace. Because, for example, you can just print the entire thing out of plastics. So it's going to be really cheap if we can achieve that. And also it's compliant mechanisms, so they don't have living hinges or require lubrication. So they are a lot more robust in harsh environments, for example. And again, we're interested in developing computational tools to support the creation of these devices. But I'm gonna skip this because it's more or less similar to what we had in the VR slide. And this is one of the examples we have developed. So in this case, the user actually is missing one joint here on their thumb. So they actually have problem or have trouble moving their thumb. But in this case, we're creating what we call a prosthetics to recreate that thumb joint, so that it makes the user easier to hold on to different objects, because thumb is actually important to holding objects if you didn't realize that yet. And in this case, we're just using a servo motor to move the thumbs. But imagine in the future, we can develop this into, like we can actuate this thumb by using, say, shared memory alloy or liquid crystal elastomer. And we can even detect like the muscle signals on the user to actuate the joint. So things like that might be interesting to look into. And we're also interested in making a whole arm wearable device for selective muscle training. For like, for example, a stroke patient might need to rehabilitate their muscles, and we're looking into that as well. So in this case, this is a scaled model of an arm, and we actually have a wearable compliant mechanism device with stiffness changing flexures to tune the stiffness of the joints. So by default, everything is rigid, and there's actually a weight attached to your arm, so everything is rigid, so it's really hard to deform. But you can selectively soften the stiffness changing flexures one by one to instate different joint stiffness to, for example, if you're training your muscle, you want the stiffness or resistance to be progressively increasing. So at the beginning, you might start with something like a low stiffness and step-by-step work your way up to a much stiffer joint, and that helps you to progressively train your muscles. And there are also a concept of workforce empowerment, meaning that we're also interested in using these wearable devices not just for patients or rehabilitation or VR AR. We can also use them for workforce empowerment, meaning, for example, we can create a compliant mechanism wearable device for workers to prevent injury. So for example, if you're painting the ceiling, you might have to raise your arm high all the time, but you can design a reconfigurable compliant mechanism exoskeleton to release the stress of raising your arm all the time that prevents injury. And compliant mechanisms are specifically favorable because they are, as I mentioned, resilient against harsh conditions, which actually happens a lot in work environments. So that's kind of needed. And in these diagrams, I'm just showing that we're also interested in introducing simulation as a part of these wearable devices to capture how they're being used. So we can use that to log, for example, the work condition of the workers, or to predict, for example, when the device will fail. And if you can predict like when a device will fail through simulations, you will be able to prevent a lot of injuries as well. So I think that's it for my lecture today. And I don't have anything more. Do we have any questions here?